Black holes might not truly have an inside. I know how that sounds. It sounds like we're throwing out Einstein or claiming there's a literal wall at the event horizon. That's not what we mean. What we mean is subtler, and honestly more unsettling in a complete theory of quantum gravity. The black hole interior may not be a separate place where new, independent information is stored. The inside could be a derived description, something that emerges when you organize the physics in the right way. And in a minute, we'll hit the clue that forces this conversation. A black hole's entropy, its information capacity scales with surface area, not volume. If that's true, then our usual mental picture of space inside a sphere may be the wrong starting point. So let's slow down and define the claim carefully. When we say black holes have no interior, we do not mean you bounce off the horizon like it's a solid shell. We do not mean nothing can fall in. And we do not mean general relativity is useless. In classical general relativity, a black hole very much has an interior region. Cross the horizon and, according to Einstein's equations, the geometry continues. There's more space-time in there. The claim often associated with ideas pushed by physicists like Leonard Susskind is about what's fundamental versus what's emergent. The interior may be real in the same sense that many everyday things are real. Real as a stable, predictive description, but not the deepest layer of the universe's bookkeeping. If that sounds like philosophy, good, because physics, at the edges, becomes extremely picky about what real means. Here's an analogy that will matter later: temperature. Temperature feels like a basic property of the world. You measure it, you react to it, you can't ignore it. But temperature isn't a microscopic object. No one has ever found a temperature particle. Temperature is a summary, a macroscopic variable that emerges from countless molecules moving and colliding. It's real, but it's not fundamental. Or take the icons on your phone. When you drag a file into a folder, it feels like you moved an object into a container. Under the hood, you change patterns of electrical states. The folder isn't fake, your computer's behavior is reliably organized around it, but it's not the lowest level description of what's happening. Keep those examples in your pocket, because the open question is this: could space-time itself sometimes behave like that? Not imaginary, just not the bottom layer. Now for a quick mental experiment. Imagine you walk into a museum with a strict rule. You're not allowed to go inside the galleries. You can only stand in the hallway that wraps around the exhibits, but the museum staff hands you a perfect, complete catalog describing every painting, every sculpture, every placement, every lighting condition, everything. If the catalog is truly complete, then in principle you could reconstruct the entire interior experience without ever stepping inside. So what would inside mean in that case? It would still be a meaningful concept for visitors. But at the deepest level, the information would already be captured at the boundary. That's the kind of possibility black hole physics starts to hint at, because black holes aren't just gravity, they're where gravity collides with quantum mechanics. In quantum physics, there's a core expectation, one that's held up incredibly well, that information is not destroyed. You can scramble it, you can spread it out, you can hide it in complex correlations. But the underlying evolution for an isolated system keeps the total information intact. Classical physics is more casual. Burn a book, and in a sense the story is gone. The ashes don't contain the novel in any practical way. Now place a book near a black hole. From the outside, it looks like the book falls toward the horizon, slows down, dims, and fades. From the book's point of view, it crosses the horizon in finite time and continues inward. Two perspectives, already a little strange but manageable. Then Stephen Hawking added a new ingredient: black holes are not perfectly black. Quantum effects allow them to emit radiation. Over immense timescales, they can evaporate. And that creates the famous problem: if the black hole eventually evaporates away, what happened to the information and everything that fell in? Does it disappear from the universe? If yes, quantum theory seems to break. If no, then where was the information stored? And how did it get out? Hold that question. We're going to return to it. But first we need one number, a number that changes everything. In the 1970s, Jacob Bekenstein and Stephen Hawking discovered that black holes behave like they have entropy. Entropy is roughly a measure of how many microscopic configurations correspond to the same macroscopic appearance. If two objects look identical from the outside, but they could be built from many different microarrangements, the entropy counts those possibilities. Here's the shock. A black hole's entropy is proportional to the area of its event horizon, not the volume inside. The area, if you're used to ordinary objects, that is backwards. For normal matter, the number of ways to arrange the stuff inside scales with volume. In bigger box, more room, more microstates. But black holes seem to max out. They're like the densest possible storage devices nature allows, and the storage limit scales like the skin. So ask the uncomfortable question. If the information capacity scales with area, is the inside actually where the information lives, or is the horizon doing the accounting? This is where the phrase holographic principle enters. A hologram is a 2D surface that can encode a 3D image. The holographic principle, in physics, is the idea that a region of space might be fully describable by data living on its boundary. The boundary doesn't just surround the region. In a deep sense, it may contain the complete description. Now, to be clear, holographic does not mean fake. It doesn't mean we live in a cheap projection. It means the fundamental degrees of freedom, the independent bits of reality may scale like area, and a boundary-based description might be complete. So return to the black hole. If the horizon carries the bookkeeping, then the black hole interior might not be an independent vault of information. The interior could be something we reconstruct, something emergent when we translate the boundary data into a space-time story. At this point, a reasonable person asks, is this just a metaphor, or is it actually true somewhere in physics? There is one setting where we have an extremely strong proof of concept. It's called AdCFT, proposed by Juan Maldacena. Here's the intuition. AdCFT says that a theory with gravity living in a bulk spacetime can be equivalent to a quantum theory without gravity living on the boundary of that spacetime. Two very different languages. One was gravity and extraspatial depth. One without yet, they describe the same physics. In that framework, bulk objects, including black holes, have a complete description in the boundary theory. In other words, the boundary is not merely a shadow. It's the full story, written in a different code. Now, the important limitation, our universe is not exactly the kind of space-time used in the cleanest versions of AdCFT. So we cannot honestly say, this proves our universe is holographic in a direct way. But it does prove something profound. It is possible for a lower dimensional, non-gravitational quantum system to encode an entire higher dimensional gravitational world, including what feels like interior space. So when someone says maybe black holes have no interior, one careful translation is the fundamental description may live on degrees of freedom associated with the boundary, and the interior spacetime is a derived concept. Now we can come back to the information paradox. If the complete description is quantum and unitary information preserving, then black hole evaporation does not erase information. Instead, information is returned in an extremely scrambled form, spread across Hawking radiation in subtle correlations. It's not that the radiation carries a readable message like a radio broadcast. It's more like a shredded book mixed into a hurricane of confetti, recoverable in principle, not in practice. This direction has become the dominant expectation among many physicists, though details remain actively researched. And now we hit the most human question in this whole story. If the fundamental ledger is on the boundary, why does the interior feel so real to something falling in? Because emergence can be stronger than intuition. A wave is not a fundamental object. It's a collective motion of water molecules. Yet if you're surfing, the wave is not optional. It can lift you, spin you, throw you. The wave is real at the scale where your body interacts with it. In the same way, the interior spacetime may be the right effective description for an infalling observer, even if the deepest accounting of information is boundary-like. This is also where the story gets delicate, because there are tensions. One tension is sometimes summarized like this. From the outside, information must come out if quantum mechanics is respected. From the inside, the horizon should feel uneventful, no drama if general relativity holds locally. Can both be true at the same time? Physicists have argued for decades. Ideas like black hole complementarity, firewalls, and more recent island calculations are attempts to reconcile these requirements. Some of these ideas are better supported than others, and the field is still evolving. So let's be ethically precise. Established, black holes have Hawking radiation in theory, black holes have entropy proportional to horizon area, holographic reasoning is strongly motivated, AdCFT is a mathematically precise duality in specific spacetimes. speculative or developing, the final, universally accepted story of what the interior is in all realistic situations, how to describe the interior during evaporation in a complete theory, how directly our universe implements holographic principles. But even with that caution, the big message survives. The area law is not a small detail. It's a billboard. It suggests that the number of fundamental degrees of freedom inside a region is limited by the boundary. And black holes appear to saturate that limit, which makes them the sharpest tool we have for probing what space-time is made of. So, what are the implications of saying black holes have no interior? First, the event horizon may be less like a passive border and more like an active information interface. Not necessarily a physical membrane you crash into, but a place where the accounting of quantum information becomes unavoidable. Second, where something is may not be as fundamental as how something is encoded. In holographic setups, location is emergent. The interior can be reconstructed from patterns in the underlying quantum system, rather than being a container filled with separate independent bits. Third, the interior might be a kind of translation, a useful, consistent space-time narrative that emerges from deeper quantum relationships, especially entanglement. Geometry, in this view, is not the stage. It's the script we infer after the underlying cast is already connected. And that brings us back to the opening line. Maybe black holes don't have an interior, not in the naive, classical sense of a volume containing stuff. Maybe the deepest truth is that the black hole is, in some sense, made of its boundary information. And inside is what that information looks like when we describe it using the language of space-time. If that feels like it changes everything, that's because it might, not because the interior is meaningless, but because it suggests the universe may be built from a different foundation than geometry. Space could be an emergent convenience, like temperature or a user interface, powerful, reliable, and real at our scale, yet not the deepest layer. So the next time you picture a black hole as a cosmic pit with a huge hidden cavern inside, try a different image. Try a surface that does far more than mark an edge. A surface that quietly contains the full accounting of what fell in. A surface that forces us to confront the possibility that once sounded impossible, that sometimes, in physics, the boundary is the thing. If you want more slow, intuition first science documentaries like this, no equations, just the ideas that reshape how we picture reality subscribe. And here's the question to leave in the comments. If space inside a black hole is emergent, what do you think is more fundamental space-time or information?